Your lecturer is Dr. Bruce H. Edwards. Dr. Edwards is professor of mathematics at the University of Florida, where he has won a host of awards and recognitions. He was named Teacher of the Year in the College of Liberal Arts and Sciences and was selected as the Distinguished Alumni Professor for the U of F Alumni Association. Professor Edwards' co-authored mathematics textbooks have earned awards from the Text and Academic Authors Association.
Hello and welcome. My name is Bruce Edwards, and I hope you will enjoy our 36 lectures together. So just what is Calculus 2? At one level, it's the content of second semester university level calculus. And that turns out to be equivalent to the Advanced Placement BC program. But what really is Calculus 2? I think we're comfortable with Calculus 1. In Calculus 1, we studied limits, and then we moved to derivatives, and then to integrals. And Calculus 3 is also pretty easy to describe. It's basically calculus applied to 3 dimensions, to space. So what is Calculus 2? Let me begin by saying it's more than just derivatives and integrals. You might remember in our study of Calculus 1 that we used a limit machine, where we took all kinds of pre-calculus ideas and put them through a limit process. Well, in Calculus 2, we'll expand on some of these limit ideas. We'll see more applications that are related to Calculus 1. But then we'll use this limit idea to explore a brand new topic called infinite series. And without a doubt, it's my favorite topic of all. And I think you'll really enjoy the portion of the course where we cover infinite series. In particular, I can list some of the organization now of our Calculus 2 course. There are basically 3 parts. In the beginning, we'll talk about more integration and differentiation applications. We'll talk about differential equations, applications like work and centers of mass, and we'll also study more methods of integration, techniques for finding antiderivatives. And then we'll move to what I think is the most interesting and fun part of Calculus 2, and that is infinite series, adding up an infinite number of numbers. And we'll see this is intimately related to the functions we've learned to love in pre-calculus and elementary calculus. And then the third portion of the course is kind of a mixture of topics that all blend together to give a full understanding of motion in the plane. These topics like vectors, parametric equations, polar coordinates, conics, etc., will also be very important if you go on and study third semester calculus. But before we begin Calculus 2 and the new topics I talked about, I'd like to devote 3 lectures, these first 3 lectures, to a review and a look back at Calculus 1. In this lecture, I'd like to talk about functions and limits, and then in the second lecture, differentiation, and in the third lecture, integration. And we will point out some upcoming Calculus 2 topics as we proceed in our review. Okay. How does one succeed in calculus? What are the key study tips that one is concerned about when one is entering the field of calculus, and in fact in any mathematical field? Well, my number 1 study tip, actually my first 2 study tips, are as follows. Number 1, practice. It's really important to practice your calculus skills. And fortunately, we have a guidebook which has some problems you can try, some exercises related to the lecture topics, and the solutions are in that guidebook as well. But second of all, and also very important, are strong pre-calculus skills. We'll see as we progress that many of the calculus difficulties are not caused by calculus. They're actually caused by algebra and trigonometry. So we have to have a firm understanding of those two topics in order to be successful in calculus. Okay. I also plan to have list a number of pitfalls, mistakes that I see students making in my experience as a professor at the University of Florida. Here are my top 10 pitfalls in calculus. All of these pitfalls actually are pre-calculus pitfalls, but they influence our study of calculus so much that I'd like to point them out. So here are the top 10 pre-calculus pitfalls. Number 10, make sure your graphing calculator is in the correct mode. Generally speaking, we use radian mode in calculus. Number 9, notation. There's lots of funny notation in calculus and pre-calculus. For instance, f to the minus 1 of x does not mean 1 over f of x. For instance, sine to the minus 1 of x is not 1 over sine x. In fact, it's the inverse sine function. Pitfall number 8. Infinity is not a number. It's sort of a concept. Never write an interval with the infinity symbol with a closed bracket. It should be an open parentheses there. Pitfall number 7. You can't divide by 0 in mathematics. You might have seen this in the famous limit sine x over x as x tends to 0. That limit equals 1, if you remember. And notice you can't just plug in 0 because the denominator would be 0, and so the numerator, in fact. So in general, don't divide by 0 in mathematics. Pitfall number 6. Your answers can appear in different forms. Here's a typical case. You might see an answer in the back of the book that says the answer is logarithm of the absolute value of secant theta. Well, by logarithmic properties, that's equivalent to minus log absolute value of cosine theta. So if you have that second answer, you're correct, even though the back of the book has a different form of that correct answer. Pitfall number 5. Be careful when you're manipulating radicals. For instance, the square root of 4 equals 2. But if you do the following, you'll get a different answer. It'd be the square root of minus 4 times minus 1. That's a fair thing to do. 4 equals minus 4 times minus 1. But the square root of that product is not the product of the square roots, because you get the square root of minus 4 times the square root of minus 1. Those are square roots of negative numbers. And if you've studied complex numbers, you know that first one's equal to 2i, and the second one's equal to I. Multiply those together, you get minus 2. Moral of the story, be careful with radicals. Number 4, pitfall number 4, be careful with exponents. Here's a very common mistake. I'll illustrate it with an example. 2 cubed times 2 to the 4th is not 2 to the 12th. You don't multiply the exponents, you add them. So it's 2 to the power 3 plus 4, or 2 to the 7th. And in a similar vein, be careful with logarithms. Here is pitfall number 3. The log of a sum is not the sum of the logarithms. In fact, the correct formula for positive numbers a and b is log of a plus log of b equals log of their product ab. Number 2, you can't split up denominators. For instance, 1 over 3 minus cosine x is not 1 over 3 minus 1 over cosine x. You can split up numerators, but not denominators. And finally, my top number 1 pitfall, logarithms can be confusing. In particular, log of 0 is not even defined. The log of e is 1, and the log of 1 is 0. Okay, let's now move on. Let's talk about functions for a moment. Functions play a crucial role in all of mathematics, and in particular in pre-calculus and calculus. I carry a lot of functions with me. They're in my back pocket. And I'd like to show you what's in my back pocket. These are a whole lot of functions that appear all the time in calculus. So let's talk about our set of functions that we've learned to love in calculus. Perhaps the simplest example are lines. lines of the form y equals mx plus b. Here m is the slope of the straight line and b is the y-intercept. For example, here's a typical equation of a straight line. Y equals 3x minus 5. What's the slope? 3. Good. What's the y-intercept? Correct. 0 minus 5. Okay, let's push it up a little bit. What if you wanted to find the equation of a line parallel to this line, but passing through the point 0, 1, a different y-intercept? What would the answer be? Well, the slope would be the same because they're parallel, but now it would be y equals 3x plus 1 because we have a new y-intercept. And you can see that that line has moved up because the y-intercept has changed. What if we wanted a line perpendicular to our given line 3x minus 5? What would its slope be? Right, the negative reciprocal, minus 1/3. I also carry around polynomials. And in particular, the two most important polynomials in my mind are the parabola y equals x squared and the cubic polynomial y equals x cubed. Y equals x squared is a parabola opening upwards, and y equals x cubed has that nice shape that you see in the diagram. Knowing the behavior of these two polynomials, you can then use calculus skills to analyze more complicated polynomials. For instance, y equals 5x to the 5th minus 4x cubed plus pi times x minus 17. The general shape of that curve, if you graph it, will be smooth. It'll go up and down, and using calculus skills, you can find out where it's increasing and where it's decreasing. You can also talk about its concavity. And these are all ideas from elementary calculus. All right, what else is back here in my back pocket? Well, radical functions. The square root of x, y equals square root of x, and y equals x to the 1/3 power, the cube root of x. Now these are quite important. Let's be clear about their domains. The square root function in elementary calculus means that x has to be non-negative. The square root of 0 is 0, and then you are not allowed to take square roots of negative numbers in elementary calculus. If you go on and study complex numbers, then you'll be able to do that. But for us, the domain of the square root function is x greater than or equal to 0. On the other hand, the cube root function has a domain of all real numbers. And you can see that in these pictures. Here's a graph of the square root function and the cube root function, and notice how their domains differ quite a bit. One thing to point out here that I think is quite interesting, the cubing function f of x equals x cubed and the function g of x equal x to the 1/3 are inverses of each other. What does that mean? That means if you compose f of g of x, you end up with x. In other words, if you first take the cube root of a number and then cube that number, you come back to where you started from. And the same is true on the other way. If you first cube a number and then take its cube root, you come back to the same number you started with. What does this mean graphically? Well, if you graph the function x cubed and the function x to the 1/3, you'll see that they're mirror images of each other across the line y equals x. So inverse functions play a big role for us in calculus. We'll see some more in a few minutes. Okay, one of my favorite functions, the absolute value function. It's also in my back pocket. It's getting to be pretty full, I know. The graph of the absolute value function is a V-shaped curve, and actually it's got a sharp point down there at the origin. The slope is 1 on one side and minus 1 on the other side. This is a crucial example in calculus of a function that is continuous. I can draw the graph of that function without lifting up my pencil, but it's not differentiable at the origin. It's not smooth like a polynomial is. It's got a sharp corner there. Okay. I also carry around rational functions. These are quotients of polynomials, polynomial divided by polynomial. And perhaps the simplest is the function y equals 1 over x. Okay, there are a lot of features of this function that are quite interesting. Here's the graph of y equals 1 over x. Notice that as x gets larger and larger in the positive direction, the graph is approaching the x-axis. In other words, y equals 0 is a horizontal asymptote. And there's also a vertical asymptote at x equals 0. And this generally is true of most rational functions. They have horizontal and vertical asymptotes. And using elementary calculus, you can find those asymptotes even for more complicated functions, like the following: f of x equals x cubed minus 3x plus 1 over x squared minus 4. Using calculus techniques, you can find the vertical and horizontal asymptotes of that function, and that'll aid you in drawing its graph. And of course, we have the trigonometric functions. These are very, very important in all of calculus. You'll recall there are 6 trigonometric functions: sine x, cosine x, tangent x, and then the functions cosecant x, secant x, and cotangent x. The graphs of these functions are periodic. They repeat themselves. And perhaps the 2 most important are the graphs of sine x and tangent x. Here's the graph of sine x. Notice its periodicity. The period is 2 pi. It repeats itself every 2 pi units. It also passes through the origin. Sine of 0 is 0. And here's the graph of tangent. It's a very interesting graph in that it has vertical asymptotes at pi over 2, 3 pi over 2, minus pi over 2, etc. And then there are trigonometric identities. The fundamental identity is sine squared x plus cosine squared x equals 1. We'll use that quite a bit. And we'll use a related identity: tangent squared plus 1 is secant squared. Here are 2 more identities you might not have seen before that will be important for us. These are called the half-angle formulas. Sine squared x equals 1 minus cosine 2x over 2, and cosine squared x equals 1 plus cosine 2x over 2. We'll use these again in some subsequent lectures, and I'll remind you what those formulas are. Okay, now that we're on trigonometry for a moment, let me pause and talk about limits for a moment. You've probably remembered this very important and famous limit: sine x over x as x approaches 0. And that equals 1. Now, what does that mean? It doesn't mean that when you plug in 0, you get 1, because you can't divide by 0, can you? So what does it mean to say that the limit of sine x over x equals 1 as x approaches 0? It means the following: that as x gets closer and closer to 0, that quotient gets closer and closer to 1. In fact, it means a subtle difference. You can get as close to 1 as you would ever desire by suitably picking x close to 0. So keep this limit in mind. We're going to use it in our next lecture. And here's a related limit we'll also use. It's the limit of cosine x minus 1 divided by x as x approaches 0. What does that limit equal? Well, you might have seen this in your calculus studies. It turns out that limit equals 0. And again, we'll use that limit a bit later. Okay. These limits and continuity are quite subtle at times. Let me point out an example that I think you'll enjoy about taking limits and being a bit careful. Let's look at the function x squared minus 1 over x minus 1. Now, what's its domain? Right, all x except x equals 1. You can't divide by 0. What's the limit, though, as we get closer and closer to 1? That limit might exist even though it's not defined at 1. And the way you can analyze that is you can factor the numerator into x minus 1 times x plus 1, all divided by x minus 1, cancel out the common factor x minus 1, and our function equals now x plus 1, except of course we have to remove the point x equals 1. This is a line with a hole in it. It's the line x plus 1 with a hole when x is 1. What's the limit as x approaches 1? Well, the limit would be 1 plus 1 or 2, because the limit of that quotient is the same as the limit of x plus 1. And now we can plug in 1 and we get the answer of 2. In other words, the hole when x is 1 wants to be filled in with the value 2. Okay, good. There are also inverse trigonometric functions. And I'd like to pause and talk about them for a moment. They're a bit tricky, I find. Let me remind you how we define the inverse trigonometric functions. There are, of course, 6 of them, one for each trig function. Let's talk about, say, the sine function and its inverse. Well, the first thing you have to remember is the sine curve goes up and down like this. It's not a one-to-one function. It doesn't pass that horizontal line test. In other words, as the sine function stands by itself, it doesn't have an inverse. But if you restrict the domain of the sine function to the interval minus pi over 2 to pi over 2, as indicated in the figure, then that piece of the sine function is one-to-one. So sine is one-to-one on this restricted domain. And now we can define the inverse sine function, which is often called arcsine. Here's the formal definition. Y equals arcsine x, or sine to the minus 1x, if and only if the following is true. Reverse the variables, x equals sine y, and now y is restricted to minus pi over 2 to pi over 2, and x is between minus 1 and 1. Remember, the sign of any number is always in that sandwich between minus 1 and 1. So the domain of the arcsine function is minus 1 to 1, and its range is minus pi over 2 to pi over 2. In fact, I invite you to graph the sine function and the arcsine function on your calculator. They're both there. On most calculators, you'll have a button for the sine function, and then right above it or right next to it, you'll have a button for the arcsine, the inverse sine function. And you know, I love calculators. I think they are wonderful devices for understanding calculus better. They draw important pictures of the graphs we're studying, and you can verify many of the results that we do here with pencil and paper by going to your graphing calculator and drawing a picture. So I'll call on graphing calculators quite a bit, and if you don't have one, of course, you can use computer programs as well. Okay, there's another very important inverse trig function I'd like to look at, and that's the inverse tangent function. Now, you'll recall that the graph of the tangent function was not one-to-one either. It was periodic. It had those pieces. So to begin to define arctangent, the inverse tangent function, the first thing we have to do is restrict the domain of the tangent function between minus pi over 2 and pi over 2. So with that restricted domain, we have the definition of arctangent. Y is arctangent x if and only if x is tangent y, reversing the variables, and here x is between minus infinity and infinity. In other words, x can be any real number, but y is in that sandwich between minus pi over 2 and pi over 2. Now here's something very interesting about the graphs. Remember, our tangent graph had 2 vertical asymptotes, didn't it? At minus pi over 2 and pi over 2. Well, what will happen when we define the arctangent function and graph it? Well, those vertical asymptotes will become horizontal asymptotes, won't they? So the arctangent function has 2 horizontal asymptotes, one at pi over 2 going out to the right, and one at minus pi over 2 going out to the left. Isn't that interesting? We'll use this little fact about arctangent later on in our lectures. These inverse trig functions will play a big role when we talk about advanced techniques of integration. In other words, finding antiderivatives. The inverse functions will appear over and over again as we do our integration techniques, in particular trigonometric substitution and trigonometric integrals. Okay, what else do I carry around in my back pocket? It's almost full. Well, there are the logarithmic and exponential functions. Okay, the natural logarithmic function, ln of x, that's the log to the base e. There's also a logarithm to base 10 on your calculator, but in calculus we generally use log base e, ln of x. And its inverse, the exponential function, e to the x. And you'll see the pictures of these two functions, and notice because they're inverses, they are symmetric across the line y equals x. Now, the logarithmic function has properties that we're very comfortable with from our pre-calculus days. For example, the log of a product is the sum of the logarithms, here assuming, of course, that a and b are both positive. And the log of a quotient is the difference of the logarithms. And a third property that's very, very important, we'll use it quite a bit in our applications, is the log of a to the b power. If you have a power hiding up there, that can motor down into the front. That equals b times log of a. Okay, here, you be the teacher for a moment. A student comes up to you and says, "Professor, why does e to the log x equal x? Why is that true?" How would you answer that? Well, yeah, those are inverse functions. If you log a number and then take e to that power, you'll come back to the original number. In a similar vein, log of e to the x power equals x. Isn't that interesting? In both cases, we're using the fact that log and exponential are inverses of each other. They undo each other. Now, who's this number e? It's about 2.718. It's on your calculator. E to the x is on your calculator. There are many ways of defining the number e, and let me remind you of a limit definition you might have seen before. It's the following. Take the expression 1 plus 1 over x to the power x as x goes to infinity. If you plug in large numbers of x, you'll get closer and closer to e. Isn't that interesting? But let me take it up a notch. Let me stretch our minds a bit. When we talk about infinite series, what I mean in street language is adding up an infinite number of numbers. There's another definition of e that appears in textbooks. It's the following. Consider the summation 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial and so on. Now, who is this factorial guy? Right, 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. 5 factorial, 5, 4, 3, 2, 1. So I think you see what these terms are. Well, as you add up more and more terms, that sum gets closer and closer to e. Wow. And we will show that in lectures that come when we study infinite series. Now, if you open a calculus book, you'll even see some more functions. I don't carry these around too much in my back pocket. It's already kind of full. But there are functions called hyperbolic functions, sinh of x and cosh of x. These functions are very important in engineering applications. For example, the hyperbolic cosine, cosh of x, is used as a model for the very famous St. Louis Arch. But generally speaking, most calculus courses and the AP program in particular don't worry too much about these hyperbolic functions. Yeah, they're on your calculator, they're there, but they're often pretty well hidden. Okay, let's go back to limits for a moment. And I'd like to lead into our next lecture with an example. Suppose you wanted to find the slope of the tangent line at a point on the sine curve. So consider the curve f of x equals sine x, and pick a point xy. What's the slope of the tangent line at that point? Here's what I'm talking about. I have the point x sine x on the graph of the sine function, and I want to find the slope of the tangent line at that point. Well, how could I do it? We'll take a nearby point. Let's call it x plus delta x, where delta x is a small number, and then form the difference quotient to find the slope of the line joining x sine x and the other point on the sine curve, x plus delta x, comma, sine x plus delta x. Well, what is that slope? It's difference in the y's over difference in the x's, sine of x plus delta x minus sine x, that's the difference in the y values, divided by x plus delta x minus x, and that simplifies to delta x in the denominator. The exact slope would be the limit of that quotient as delta x goes to 0. What do you think it is? Well, next lecture, we'll find out the answer. We'll actually calculate that limit. But here's a hint. Next lecture is on derivatives. So what do you think that limit is? I'll see you next time with the answer.